So we're looking at complex numbers. So what is a complex number? And solving quadratic equations where some of our solutions might be complex numbers. In the past, when you have gotten a negative number under a square root, like for instance, the square root of -9, we would say that there was no solution or no real number. This is actually an imaginary number. The square root of -1, by definition, is equal to what we call I. So knowing that, I could break this down, the square root of -9, I can break it down as the square root of -1 times the square root of 9 equal to I, and usually you write the I second, I times 3, or usually you write it 3I, but they mean the exact same thing. So notice, like we were doing, I believe, was that yesterday? Actually, I think we're taking the opposite. We are taking the square root. Anyways, if we wanted to get rid of the radical, because this is an equation, we could square both sides of our equation. So if I squared both sides of this equation, notice square root of -1 quantity squared, that cancels out and we're just left with -1 is equal to I squared. Okay, so that's another definition that we need. So a couple things that you need to remember is that the square root of -1 is equal to I by definition, and that I squared is equal to -1. So a lot of times we're working with real numbers. What inside the real number system are little subsets of that system, like integers, whole numbers, rational numbers. The complex number system actually is greater than the real number system, and the real number system is a subset of that. And so the complex number system, or complex numbers, they're written in the form of a plus little b I. And we say that a is equal to the real part of that number. And we say that b is equal to the imaginary part. So for example, oops. If we had 2 minus 3i, and it asked you what is the real part and what is the imaginary part. So the real part is the number without the I, and the imaginary part is the number coefficient in front of the I. And make sure you're carrying the sign. So in this case, the real part we would say is 2. And the imaginary part in this case is -3. So if I had the example where I'm asked, if I had -10 and it asked what is the real part and the imaginary part. Well, notice there's no I in there. And so we can think of this as, if we wanted to, instead of -10, we can think of it as plus 0i. 0 times anything is 0. And so our real part is -10, but since there was no I in there, it's 0. Okay, so the complex number system is actually quite amazing. We're not going to see it here, but there's a lot of times upper division math where you can't solve things in the real number systems, and if you convert it into a complex number, you can actually solve things and things come out really easily. And so a lot of mathematics I found is manipulating things to make them easier so that it just falls out and you get what you want. Okay, so operations of complex number systems is basically the same thing as adding real numbers, and treat it when you're adding the real number parts together and you add the imaginary parts together. When you're summing the imaginary parts, it's just like you're adding like terms. So for an example, if you had, let's say, 5 all times the quantity 6 minus 2i, and this is minus 3 all times the quantity 9i minus 1. And so it asks us to simplify, let's say the directions are simplify the following expression and identify what the real and the imaginary part are. Okay, so notice this, and I expressed that I was saying expression. This is an expression, so we're not solving for anything. We're just simplifying things down as far as possible. And so we're doing order of operations. Notice inside the parentheses, that's usually where you go when you're doing order of operations. Those are not like terms, and so we cannot simplify that any further. And so now we're going to go to multiplication, our distributive property. And so we can distribute the 5 to each term inside the first parentheses. And so distributing that 5, I get 5 times 6 is 30, minus 5 times 2i. So just multiply the real parts together. 5 times 2 is 10, and then I. Distribute, carry the sign when you're distributing it, the -3. And so distributing -3 times positive 9i, well, -3 times 9 is -27, and then the I. And we have -3 times -1. Well, negative times negative is positive, so +3. So we can simplify this because we can combine like terms now. So combining like terms, we have 30 minus, oops, 30 minus, not 30 minus, 30 plus 3, which is 33. And then adding our imaginary parts, we have a -10i minus a 27i. Signs are the same, so add 10 plus 27 is 37, carry the same sign, so -37 or minus 37i. And so looking at it, we can define which part is real and which part is an imaginary. So the real part is 33 and the imaginary part is -37. Okay. You should also be able to multiply complex numbers. And when we're multiplying complex numbers, just remember that I squared is -1. So whenever we see an I squared, we're going to replace it with -1. And so let's say we had, I could just pull things out, 7 minus 4i, all times 2 plus I. Okay, so using our distributive property, looking at the first term in the first parentheses, distribute it to each term in the second parentheses. So 7 times 2 plus 7 times I. So this gives us 7 times 2 is 14 and 7 times I, so plus 7i. Go to the next term in the first parentheses, which ends up being -4i, and distribute it to each term in the second parentheses. So -4i times 2 is -8i, and -4i times I. So that's -4i squared. But again, I squared is -1. So we can rewrite this. This is 14 plus 7i minus 8i. We might as well combine those. So 7i minus 8i is -1i, or -i minus I. And this is -4 times -1. So 14 minus I, negative times negative is positive, so plus 4. We can still add real parts. 14 plus 4 is 18 minus I. Okay, so the last thing in this for operations is division. And so in division, we don't like I in the denominator. And so to get rid of the I in the denominator, we want to multiply by the conjugate of that complex number, both to the numerator and denominator. We want to make it a fancy one. So sorry. Trying to get black, but maybe it doesn't matter.
Ms. Neisler, this is Laura. I have a question. I have a question.
Yeah, Laura.
Can you hear me okay?
I can.
Oh, good. So why are you using the equal sign if this is an expression? I'm just kind of getting a little bit confused. I will use the equal sign only when it's an equation.
Okay.
And let me tell you something. I work with children with special needs at a junior high, and sometimes I get to be in math classes. So at the junior high level, they're teaching the kids don't use equal sign, and so it's just for my own sake.
Okay. Okay. Laura, I actually think that's a great question, and if you had had me 3 years ago, I would have not put that equal sign in there. It was just a comment from a colleague that had come to observe me, and he preferred the equal signs in there. And so this was going through a 10-year process, and so I put the equal signs in there. But I agree with you. I think that's a kind of confusing. The reason I'm putting it though below there like that is because those are equivalent statements. And that's basically what an equation is taking some expression that is equal to some other expression. They're just written in different forms. But I agree with you. I prefer not doing that, and I might actually change that because of that comment. So.
Okay, so for this class sake, do you want us to use the equal sign or not?
You don't have to. I'm okay with that.
Oh, okay, thank you.
Writing it without that equal all the way down.
Sounds good.
Yeah. Any other questions? Okay, so if we're gonna divide, so dividing complex numbers. You want to get the imaginary part out of the denominator. And so you're going to multiply by 1, but a fancy one. Which is equal to the let's say a plus bi all over, actually let's do a minus bi, all over a minus bi. Where a minus bi is the conjugate of the denominator. So conjugate, and you guys have used this before in the past when you're trying to get rid of radicals in the denominator. If it was like in the form of 3 plus square root of 2, you had to multiply by the conjugate of that denominator, which was changing the sign in between. And so the conjugate of a plus bi is just change the sign in between those two terms. So it's a minus bi. Okay.
What does conjugate mean?
Conjugate, it's, in this case, it's just changing the sign in between. So for instance, if I was asked for the conjugate of 2 minus 3i, the conjugate would be 2 plus 3i. And if I had maybe minus 4 plus 6i, the conjugate of that is negative 4 plus, or sorry, change the sign in between, so minus 6i. So really the purpose of that is because notice the conjugate, those kind of look like the factors of a difference of two squares. And what's going to happen is when you're squaring an I, we said that's negative 1. And so that's going to get rid of that imaginary part in the denominator. Same sort of kind of idea as when you were doing that for radicals. If you rewrote it as a factor that looks like a difference of squares, a squared minus b squared factors as a minus b, a plus b. When you square that radical, which you are trying to get rid of in the denominator, it goes away. And so we're using kind of that fact in order to get rid of what we need to in the denominator and rewriting it in a different form. And so if you had, for instance, I don't know, 6 minus 3i all over 4 plus 11i. So they might ask you, perform the following operations on this expression and write your answer in a plus bi form. So we need to have it so we have a real part together and we have an imaginary part together. So by the rule, we can do this by multiplying this expression for 6 minus 3i all over 4 plus 11i by that fancy one. And that fancy one is going to be made by taking the conjugate of the denominator. So 4 plus 11i, the conjugate is 4 minus 11i. So whatever we do to the denominator, we also have to do to the numerator. So notice I'm going to have to distribute. So I have this 6 minus 3i, that's in parentheses, so I have to distribute 6 times 4, so this gives me 24. 6 times negative 11i is negative 66i. Distribute my negative 3i, negative 3 times 4 is negative 12i, and negative 3 times my negative 11i. Negative 3i times negative 11i. Negative 3 times negative 11 is positive 33, but I squared is negative 1. So this is going to really be minus 33. So I can distribute like I just did on the bottom, or I can, again, use that fact I was talking about but didn't write down, that these look like a difference of squares. So recall, if we had a squared minus b squared, we factored that as a minus b, a plus b. Well, this is in the form of a minus b, a plus b, we could basically just square our first term minus the square of the second term. And so that's just kind of a fast way to do things. And later, when you get further in math, sometimes faster ways are helpful. Okay, so we're going to use this. I'm going to square my first term minus the square 11i of my second term. Okay, so let's combine like terms in our numerator. And combining my real part, 24 minus 33. So 33 minus 24 is 9. And the larger number is negative, so negative 9. And then I have negative 66i minus 12i, same signs, add. It's going to be minus. So 66 plus 12, that's 78i. All over 4 squared is 16 minus 11i squared. So 11 times 11 is 121, and I squared is negative 1. So 11i squared is really negative 121. So I can't simplify in my numerator because those aren't like terms. So the real part minus plus the imaginary part, negative 9 minus 78i, and then I really have 16 minus a negative is plus. So I have 16 plus 121, which is 137. Okay, so to kind of save you some heartache, that's a right answer, but it's not in the form of a plus bi because it's not in the form of the real part plus the imaginary part. So if you put that into my math lab, it's probably gonna come out probably saying that you're wrong and to rewrite it. I'll probably tell you why you're wrong too, but you wouldn't know that unless you read it. Anyways, notice because I have a single term in my denominator, let's go backwards. Normally we're trying to combine two fractions as a single fraction, but it's also helpful sometimes to rewrite a single fraction as a sum of multiple fractions. So by definition, this is the same thing as negative 9 all over 137 minus 78 all over 137 I. So I can have that I in the numerator, but really to see more of what the imaginary part is, pulling the I outside of the fraction is probably better. They mean the same thing though. Okay, so we just divided an imaginary number and wrote it in complex number form. Okay, so the last thing in this section, I believe, is solving quadratic equations like we were doing yesterday. It's just now that when you get a negative underneath a radical, you don't say there's no solution. We say there's a complex solution and we write it in the form a plus bi. So for example, so if it said solve the following, x squared plus 5 equals 0. So remember, solving quadratic equations, there's multiple ways to go about it. First thing, usually you isolate, get everything to one side of the equation, and you would see if you could factor it. Can't factor here. I could use the square root method, which is what I want to do. Or I can use the quadratic formula. I could complete the square here. So there's multiple ways, again, that you can go about this and achieve the same result. So I want to isolate. I notice I have a perfect square in here, and I can isolate my x squared by subtracting 5 to both sides of my equation. So doing that, I get x squared is equal to negative 5. And then I notice to get rid of the square, I could take the square root of both sides. And when we take the square root of both sides, we had to put plus or minus in front of the one side. So I have the square root of x squared is equal to plus or minus the square root of -5. Well, the square root of x squared is just x, is equal to plus or minus. Well, we can break this down. This is the same thing as -1, square root of -1, which is I. And then we have a 5 underneath the radical still. So x is equal to plus or minus I root 5. So there's a case right there where I was just telling you, usually you see I after the number. Here's a case you would usually see I before the number, because it's sometimes confusing. Is that I really underneath the radical or not when it's after a coefficient of the square root? So usually put that in front. So one more, let's say if you had 2x squared minus 4x minus 5 equals 0. First thing I would try to do in this instance is actually try to factor it. But I know that we're working in the section that's not going to work in this. And I'm going to have to use the quadratic formula. So I might as well just jump into the quadratic formula. So remember quadratic formula, x is equal to -b plus or minus the square root of b squared minus 4ac all over 2a. Okay, and here's my favorite way to memorize that formula, and you might have heard it before. I was actually taught this by one of my students maybe 8 years ago. So if you haven't heard this, this is cute, and I might be saying it a little wrong, and you could correct me if you have heard it. But to remember this formula, you have a negative b, so negative boy, couldn't decide, so plus or minus, couldn't decide to go to a radical party, so there's where the square root is, b squared, and lose out on 4 awesome chicks, 4ac, all to be over at 2 a.m., 2a. Okay, so I don't know if you know that, but there's one way if you don't have that memorized, because you really do need to have that memorized, that it would work. Or I've heard teachers bring in a trumpet and play Pop Goes the Weasel, but I'm not going to sing it for you. Anyways, so negative b, so we got x is equal to, so b is the coefficient in front of the x, so negative of -4, well, that's really +4, so I'm just going to put +4, plus or minus, and I really don't need that plus, the square root. So b squared, -4 quantity squared, -4 times -4 is +16, minus 4 times a is 2, times c is -5, all to be over, divided by 2 times a, which is 2.
You forgot the 4, didn't you?
I did. Did I say it? Sometimes I say things and I write, I don't know. Okay, so 4 times a, which is 2, times c is -5. Thank you. So you get 4 plus or minus the square root of 16. That's not an imaginary number. I'm just curious if I wrote down the problem differently. Okay, anyway, sorry. 4 times 2 is 8. 8 times 5 is 40. So plus 40, all over 2 times 2, which is 4. So I got 4 plus or minus the square root of 56, all over 4. Okay, so I notice I can break this down a little bit. And I can pull out a piece, square root of 56. So this is the same thing as 9 times 6, right? Gosh. No, it's not. I'm thinking 56 was a perfect square. I had a perfect square as a factor. $56 can be broken down as 4 times 14, which is going to be 2 root 14. Okay, so this is 4 plus or minus square root of 56. I can rewrite as 2 root 14 all over 4. I'm not quite done because I have a factor in my numerator that, so I have a greatest common factor between those two terms that is divisible in my denominator. So I have a common factor. So I need to pull out, I have a 4 plus 2 root 14. They both have a 2 in common for both of those terms. We can pull out a 2. And I'd be left with 2 plus or minus root 14 all over 4. And so notice now we can simplify. This 2, now that it's multiplication, cancels with this 4 down here, leaving a 2. So yeah, x is equal to 2 plus or minus root 14 all over 2. Okay, I just thought, you know, with this example, for sure I was going to have a negative underneath the radical, so I thought I did something wrong, but I didn't. And then I was trying to think to myself, how could we show that that was actually the correct answer? Anyone know? So again, that's just something, and we kind of looked at this, I think yesterday, where I said, okay, these are our solutions. What would one of the polynomials look like that this would be a solution of? It's kind of the same idea here. We know 2 of our solutions. We could figure out what polynomial these were solutions of. So, and maybe I shouldn't spend that much time on it, but basically, let me just set it up for you, because we will be doing this actually later in the course. So remember, x equals, I'm going to write this as 2 plus root 14 all over 2. That's one solution. And then the other solution we can write as x is equal to 2 minus root 14 all over 2. So if that is a solution, we can figure out what the factor is of a polynomial. So if we subtract this constant, which is an ugly constant, but it is a constant, from both sides of the equation, we would get x minus this quantity 2 plus root 14 all over 2. And on this one, we would have x minus that whole quantity 2 minus root 14 all over 2. So if I took this, which is a factor of my polynomial, and this, which would be a factor of my polynomial, and I multiplied those out, I should get back our original piece. which was 2x squared minus 4x minus 5. Okay, just make sure that it covered everything. So you should be able to add, subtract, multiply, and divide complex numbers. Out of all of those things, division shows me that you know how to do all 4 of those, because in there you know how to multiply. You're multiplying by the conjugate. You know how to add like terms, so real and imaginary part. So if I had to test you on a problem, or if I tested you on that, it will be division. And then you should be able to solve quadratic equations in the complex number solution system. So basically, if you had used the quadratic formula and you got a negative underneath the radical, that's in a complex number, you would have I in there. Okay. So I think I'm gonna change a sheet and see if you guys have any questions before we go on to the next section. Okay, so there's no questions on that last material, and now we're jumping into 1.4, which is solving equations that have radicals in them, and then also solving equations that could be manipulated to be a quadratic equation. So they're called quadratic in form. So equations that have radicals, it depends on, is there more than one radical or not? So, but you're always going to start out the same way. So I guess, let's just write this. So your recipe on solving radical equations, first step you want to do is you want to isolate one of the radicals to one side of the equation. So we're getting everything else besides that one term with a radical to the other side of the equation. And so once you've done that, we can raise both sides of your equation to the power that would cancel out what root you were taking of that radical. So you're gonna raise both sides of your equation. Oops. By the index of your radical. So what the index is, remember, it's that number here. So if I have this as the nth root, n would be my index. If you don't see a number there, remember the index is 2. Okay, so you've isolated one radical. If there was more than one, or you just isolated the radical if there was just one, you raise both sides to that index. That gets rid of the radical on the one side that you had isolated it. You're going to repeat steps 1 and 2 until no more radicals. Until there are no more radicals in the equation. And so once all of the radicals are gone in that equation, then you need to determine what type of equation. Is it linear or is it quadratic, and how am I going to go about solving? So solve the equation. And then we need to be careful because if you raise both sides by a power that's even, you might come up with answers that are not part of the solution set. So you might come up again with extraneous solutions like we were looking at yesterday, values which made our denominator equal 0. So if you raise both sides of an equation by an even power, if it's odd, then as long as our work is right, all our answers would work. So if you raise both sides of an equation by an even power, you must check for extraneous solutions. So basically, you're just going back into your original equation, plugging in that value that you found was the solution, and for your variable, and see if you get back a true statement. If you get back some false statement, then that number that you found is not part of the solution set. So I'm just going to jump to one of the harder ones that has more than one radical in there. So let's say we had the square root of 3x plus 1, which is underneath the radical. That's called the radicand. And then minus, then we have another radical. And the radicand is x minus 1 there. This is equal to 2. Okay, so the first step was we need to isolate one of these radicals. There's 2 radicals in this equation and we need to get rid of one of them, or we need to move it to the other side. I prefer to have positive, so let's just add square root of x minus 1 to both sides of the equation. So if we do that, we get the square root of 3x plus 1 is equal to 2 plus the square root of x minus 1. And so we've isolated one of the radicals. So the next part was you're going to raise both sides by the index of the radical that you had isolated. So it's a square root, so I'm going to square both sides of my equation. This is where you need to be careful. And a lot of students get this next step wrong. So the square of the square root, that cancels. We're left with the radicand, which was 3x plus 1. But here, this 2 plus the square root of x minus 1, this is 2 terms. We need to distribute this out. We can't just square each term inside that parentheses. So we have 2 plus the square root of x minus 1. All times that parentheses 2 plus the square root of x minus 1. Okay, so we need to distribute there. So bring down our left-hand side. So 3x plus 1 is equal to, and now distribute. So 2 times 2, this gives us 4. 2 times the square root of x minus 1, so this is 2 root x minus 1. Do the same thing now, distribute square root of x minus 1 times 2. So that's 2 square roots of x minus 1. And the square root of x minus 1 times the square root of x minus 1. Well, that's just square root of x minus 1 squared. The radicals cancel. So that just gives us plus x minus 1. So combine like terms on each side. Well, there's no like terms on the left-hand side, so we have 3x plus 1 is equal to, so let's look at the real parts, 4 minus 1. So 4 minus 1, that gives us 3. we can add expressions with radicals if they have the exact same radicand, what's underneath. And so we can combine 2 square root of x minus 1 plus 2 square root of x minus 1. You just add the coefficients in front, 2 plus 2. So that's plus 4. Keep the radical the same, square root of x minus 1. And then I notice I still have this plus x over here that I haven't added to anything else. Okay, so I need to repeat that step. I still have a radical in my expression, or my equation, sorry, my equation. And so I need to go through the same process and I need to isolate the radical. So let's subtract 3 on both sides of our equation. Let's subtract x on both sides of our equation. So doing that, we get 3x minus 1x is 2x. 1 minus 3, so that's minus 2, is equal to 4 square roots of x minus 1. So I personally don't like to deal with fractions if I don't have to. I could divide everything through by 4. But I also know, because that's strictly multiplication there, I can also square this. And I think it's easier just to go ahead and square it instead of dealing with fractions and squaring it. So that's what I'm going to do. So we need to square this 2x minus 2, and I'm going to square this 4 square root of x minus 1. So this gives me, again, I'm going to have to FOIL this out. 2x minus 2 times 2x minus 2 is equal to 4 squared, which is 16, all times square root of x minus 1 squared, which is x minus 1. Distribute and combine like terms. So 2x times 2x, 4x squared. 2x times negative 2 minus 4x. Negative 2 times 2x minus 4x. Negative 2 times negative 2 is plus 4 equals, distribute the 16, 16x minus 16. Combine like terms on each side. Only the left-hand side could be simplified. And so we have 4x squared. Negative 4x minus 4x, that's negative 8x, plus 4 equals 16x minus 16. So this is where you have to determine, we got rid of all of our radicals. We don't have to repeat that process again. We have to determine which process we're going to go through to solve this. So I notice this is a quadratic equation. So I'm going to set this equal to 0. So let's bring down the 4x squared. If we subtract 16x on both sides, negative 8x minus 16x. So that would give us the minus 24x. And if I need to move this minus 16 over, add 16 to both sides, 4 plus 16, so this is plus 20, is equal to 0. Okay, so it's quadratic. I would try to factor it first. I don't like that the coefficient in front of x squared is not 1, but I notice I can manipulate it to be 1 because the greatest common factor of those 3 terms on the left is 4. So let's factor out a 4 from those 3 terms. If we pull it out, we're left with x squared minus 6x plus 5 equals 0. And then I'm really happy because I see 2 numbers that multiply to give me my constant of positive 5. But if I added those 2 numbers together, I would get negative 6. Well, I'm multiplying and getting a positive, and I'm adding and getting a negative. So I know they're both negative numbers. The only two numbers that multiply to get me 5 are 5 and 1, or -5 and -1. And I add -5 and -1, I get -6. So this is x minus 1 is a factor, and x minus 5 is a factor. Set each factor equal to 0. Well, 4 is never equal to 0, so we're okay there. X minus 1 equals 0, though, when x is equal to 1. And x minus 5 equals 0 when x is 5. Okay, we're not quite done because we ended up raising both sides of our equation by a square, an even power. So we have to check our solution for answers. Okay, so x equals 1. We want to go back into the original and see if we plug in 1 for x, if we would get the same thing. I'm going to try this. Oops. Okay, so I'm going to check by plugging it back in. I just want to bring that equation down, so it made it easier. Okay, so we have the square root. We have 3. Wherever you see an x, we're going to plug in 1. So actually, I'm just going to go in there and I'm going to put in a parentheses wherever I see an x, and then I'm going to go back and replace that with 1. So I have 3 parentheses plus 1 minus the radical. I see an x there. I'm going to put parentheses there. Minus 1 equals 2. And we're actually putting a question mark above our equal sign because we're not sure. We're checking to see if that's a true statement or not. So go back into your parentheses and plug in the 1. Using order of operations, let's simplify the left-hand side. So we have 3 times 1 is 3 plus 1, so that's root 4. So it's the square root of 4 minus 1 minus 1 underneath the radical is 0. So it's the square root of 4 minus the square root of 0 equal to 2. And it is. So I know x equals 1 is a solution. And now I have to do the same thing, but now I'm doing it with x equals 5. So x equals 5. We want to go back in. Wherever we see an x in our original equation, we're going to be plugging in 5. Okay, so is the square root of 3 times x, so 3 parentheses, plus 1 minus the parentheses, or square root parentheses, because I see an x, minus 1, is that equal to 2? Plug in 5 where you put a parentheses. Okay, so 3 times 5 is 15. 15 plus 1 is 16. So square root of 16 minus 5 minus 1 underneath that radical is 4. So square root of 4 is this equal to 2. Square root of 16 is 4. 4 minus square root of 4 is 2. 4 minus 2 is equal to 2. And so they both work. And they're both solutions to that equation. So it's possible that when you go back and you plug in your solutions that none of them work. It's possible some of them work and some of them don't. It's possible they all work. So you got to go back and check. Okay, so I just kind of did one of the harder problems from that section, but again, this should be review. And basically what made it harder with this problem is that I had to go through the process multiple times to get rid of the radical. Just be careful if there's more than one term that you're squaring. You need to FOIL that out. You can't just square each piece inside if there's more than one term and you're raising it to a power. So I think this might be a good spot to take a break. So let me just pause the video and see if you guys have any questions. Okay, so we just looked at solving equations with radicals and the process of going through that. And now we're going to look at equations that are similar or could be manipulated to look like a quadratic equation. And so let me pull up a pen. For example, let's say we had the following. We have 1 all over parentheses x plus 6 quantity squared minus, actually is equal to 1 over x plus 6 plus 12. Okay, so there's multiple ways that we can approach this equation. It's a rational equation, so we could get rid of the fractions, and we could do that by multiplying by through by your LCD. I also noticed that this can kind of be manipulated to look like a quadratic equation. Let's rewrite this by getting everything to one side of the equation and setting it equal to 0. And then let's kind of manipulate it. And so let's subtract the 1 over x plus 6 from both sides of the equation. Let's subtract the 12 on both sides of the equation. And so if we do that, we have 1 all over x plus 6 quantity squared minus 1 over the fraction x plus 6, because we were getting it to the other side, and minus 12 is equal to 0. Okay, so quadratics, recall, are in the form of, ax squared plus bx plus c equals 0, or something in that form. And so I noticed I can get it in that form. Let's look at it where instead of having the square down here in the denominator, wouldn't you agree that that's the same thing as if I had squared this whole fraction? Because the square of 1 is just 1, and the square of x plus 6 would give me what I had over here. So this is the same thing as this. It's just rewritten in a little different way. So this is where we use a substitution. I tend to call it U substitution because that's what you use in calculus and the letter. But we want to use a substitution. So let's use a substitution. And so also I noticed that if you had chosen that substitution, so you can call whatever variable you want, I'm going to call it U. If we choose U to be this fraction 1 over x plus 6, let's go back now into that equation that we have, and wherever we see 1 over x plus 6, instead of that, we're going to rewrite it with a U there. So notice we have 1 over x plus 6, and that quantity is squared. So we're going to go back and we're going to replace that. So we have U quantity squared, and then we have minus, so I see the 1 over x plus 6 again, so I'm going to replace that with a U. And then I have my minus 12 equals 0. And so now it's in a quadratic form. It's one that looks pretty easy for me to solve, where the other one, that equation we started with, looked a lot harder. And so notice that this is factorable. There's two numbers that multiply to give you negative 12 and add to give you negative 1. And so that would be negative 4 and a positive 3. So u minus 4, u plus 3 equals 0. So I can solve for u in each case. I'm looking at when is u minus 4 equals 0, and I see that's when u is 4. And we're looking at when is u plus 3 equal to 0. Subtract 3, we get u is negative 3. Thing is, we're not done because we had an original equation with x, and we need to figure out what x is and not u. So we need to solve for x. Well, we had said that u is equal to 1 over x plus 6. So technically, we can rewrite this as two separate equations, one when u is 4 and one when u is negative 3, and solve this for when for x. So if we go back in here, we're looking at 4 is equal to 1 over x plus 6. And we're looking at when is negative 3 equal to 1 over x plus 6. So this is a rational equation. I can multiply both sides of my equation by x plus 6 to clear my fraction. And so doing that, I have 4 times the quantity x plus 6. And that gives me back, distribute my 4, I get 4x plus 24 is equal to, x plus 6 is cancel, 1. I need to get x by itself. So subtract 24 on both sides. I get 4x equals negative 23. Get rid of the 4 in front of the x, divide both sides by 4, I get negative 23/4. So same idea with this other equation. We're gonna multiply both sides of our equation by x plus 6 to clear our fraction. Distribute the negative 3. So negative 3 times x is negative 3x. Negative 3 times 6 is minus 18 equals x plus 3 is, or x plus 6 is cancel 1. So add negative 18 on both sides. We get negative 3x is equal to 19. Divide by negative 3, we get x is negative 19/3. Okay, so as long as I didn't make any little errors with my arithmetic or carrying things down, this is our answer. I guess there is one thing I have to check and worry about, because I do have a rational equation. I can't have any values of x which set my denominator equal to 0. So I guess x, I have to say, and it isn't one of my solutions, x can't be negative 6. So I'm okay, because these are not negative 6. Okay, so we could have solved that by multiplying by the LCD, x plus 6 quantity squared, and gotten the same result in the end. So let's look at another one. 8x is raised to the 2/3 power minus 39, x is raised to the 1/3 power, minus 5 equals 0. Okay, so we're going to try to manipulate this so that it looks like a quadratic. So you need to remember rules of exponents. And so rules of exponents you're going to be using over and over again, especially in calculus and rewriting things in this course too. But recall that power to power of an exponent, so if I had b raised to the m power raised to the nth power, that is equal to you multiply the exponents, m times n. So I'm going to go backwards. This coefficient, or this x to the 2/3 power, could be rewritten as a power to a power. Because technically 2/3 could be rewritten as 1/3, I'm gonna write it this way, power times 2, right? 2 times 1/3 is 2/3. Minus 39, x to the 1/3 minus 5 equals 0. So notice if we choose our u to be x to the 1/3 power, we now created this to look like a quadratic equation. So a trick in this class, basically all of these that you're manipulating to look like quadratic equations, if you get everything to one side of the equation like we had to do with that other problem, that term that doesn't have the square, that middle term is usually what you're going to choose, that portion to be your u. And when you go back to substitute it in, it's going to look like a quadratic. Okay, so I'm going to rewrite this whole thing so that now it looks like a quadratic. So I have 8 times, I'm going to put a parentheses where x to the 1/3 is, and I'm going to rewrite that later with a u. That quantity squared minus 39, parentheses, minus 5 equals 0. Okay, so it's a quadratic equation, and I need to see if I can factor this, or I can jump into using the quadratic formula. Either way, I notice I can factor this just because I'm looking at my AC method, which I did not go through yesterday. So just kind of a refresher. AC, if A is not 1 in front of the square, you multiply A times your constant. So that's 8 times -5. Multiplying that together gives you -40. So you're looking for two numbers that multiply to give you the number -40, but add to give you your b value, which is -39. So I know there's two numbers that multiply to give me -40, which are -40 and 1. And those two numbers, if I added them together, would give me -39. So this method, the trick is to take those two numbers you found, and instead of rewriting the middle term like it is, you're going to rewrite it as a sum using those two numbers. So I have to put in the u there. So minus 40u plus 1u. So I just rewrote it. If I combine those like terms, I'd get what I had above. And then carry down my -5 equals 0. So if you can find those two numbers, this will always work, and it is factorable. And what's going to happen is now we can use factoring by grouping. So sometimes when you can't factor and you have 4 terms, that's how you should go about trying to do that. So that's where you group your first 2 terms together and your last 2 terms together. So you pull out what they have in common in your first 2 terms. So 8 and 40, those both have an 8 in common. I can pull an 8 out. And u squared and u, you can pull u out of both of those terms. And so doing that, you're left with a single u and then minus a 5. So I notice u and -5 don't have anything in common, but I also notice it's the same thing I have in parentheses here. So think of it as just, let's think of it as factoring out a 1, and it helps some people to see the 1 there. So it keeps what we have the same, u minus 5 equals 0. So technically what you have in those parentheses are the same, so we can use factoring by pulling out the u minus 5 from both of those pieces, those groupings. And for the first piece, you're going to have an 8u left. Plus, and if you pull it out of the other piece, you're just going to have a 1 left, equals 0. Okay, so we've factored this. Now we can set each factor equal to 0, u minus 5 equal to 0, and 8u plus 1 equal to 0. Add 5 to both sides to get u by itself. You get u is 5. Here we're going to have to subtract 1, so 8u equals -1, and divide by 8, so u is -1/8. So we want to solve for x. And we know u is equal to x to the 1/3. And so we can go in here and we can substitute it in. So let's look at when u is 5. So we have 5 is equal to x to the 1/3 power. And we also have -1/8 equals x to the 1/3 power. It doesn't matter what side, we could have done the other side. So here's an example again where knowing that rule, power to power is multiplication. We don't want that 1/3 power. We want it to the first power. And so we could raise both sides of our equation. We can cube both sides of our equation to make that x to the raised to the first power. You could have also thought of that x to the 1/3 power is the same thing as the cubed root of x. And so get rid of the radical, you would have to cube both sides. Okay, so cubing 5, we get 5 cubed. 5 times 5 is 25. 25 times another 5 is 125. So we get x equals 125. And x equals, well, cubing -1/8. Let's carry the negative with a 1. So if I cube -1, -1 times -1 is +1 times -1 is negative. So -1 all over 8 cubed, which is a little more difficult. 8 times 8 is 64, times another 8 is 512. Okay, so I just need to think about a couple things to make sure I don't have any extraneous solutions that could occur. So did my original equation have a radical? I mean, I guess that actually does matter sometimes. But does it have variables in the denominator? And it does not. And then did I raise anything in here when I was going through to solve it? Did I raise both sides of an equation by an even number? Which I didn't. Over here, that last piece, if I had to square both sides, I would have had to gone back and checked this whole thing, or check it and see if it worked in the original. I'm just gonna, another just kind of review because it's really important that you remember this. So recall, if you have some value raised to a fraction, a rational exponent, this is the same thing as, you can rewrite this as a radical. The denominator of the rational exponent is what root you're taking. So in this case, x raised to the m divided by n power is the nth root. And then x, so the numerator is what power you're raising this to under the radical. It could actually be under the radical, and a lot of times it's better when you pull it out of the side of the radical, just because you don't have to deal with bigger numbers underneath the radical and figure out what root that is. Okay. Okay, so how about let's have you guys try it. Let's say you had x plus 6 inside parentheses. That quantity is squared plus 3 all times x plus 6 in parentheses, and then a plus 2 equals 0. Yeah, so try that. So there's two ways that you can do it, but, and I would love it if half the class did it one way and half the class did it the other way, just to see who was faster. So try whatever way you want. And let me know if you get an answer. Okay, so there's a couple ways to do this again. So you can distribute out x plus 6 times x plus 6. You can distribute that 3. You can then combine like terms and try to factor it that way. It's actually a lot faster if you use that u substitution. And so if you let u equal x plus 6, so let's go back in here, wherever we see this x plus 6, we're going to replace it with u. And so we get u squared plus 3 all times u plus 2 equals 0. So we've just manipulated this to look like a quadratic equation, or as a quadratic equation, and we can solve this using one of our methods. And so we're looking at what multiplies to give us 2 and adds to give us 3. So that's positive 2 and 1. So u plus 2, u plus 1 equals 0. And so now I'm looking at this and I'm setting each factor equal to 0 and solving for u. So u plus 2 is equal to 0 when u is negative 2. So sometimes I'm going to skip steps. U plus 1 equals 0 when u is equal to negative 1. And now I need to go back in and solve for x. Well, we have that u is x plus 6. So I have negative 2 equals x plus 6. And I have negative 1 is equal to x plus 6. And so if I solve for x in the first equation, if I subtract 6 on both sides of the equation, I get negative 2 minus 6 on the one side, which is negative 8. And then if I subtract 6 on the other equation, negative 1 minus 6 is negative 7. So I get x is negative 7, which were the answers some of you had gotten, which is correct. So those of you who had went and distributed out and combined like terms, you might have still been working. Or it probably took you a lot more work. Is that true? Yeah. Yeah, so a lot of times, and again, math is all about manipulating and making things simpler in a way that we can work with. And so sometimes doing tricks like this they're helpful. Okay. So I'm trying to gauge where you guys are and if I move on or if I need to do more examples of from this section. The next section moves to inequalities, which is kind of similar to what we're doing with solving, kind of like solving linear equations, but you have the less than or equal to, or greater than or equal to. So let me pause. Okay, so we've been looking at solving a lot of different types of equations and going about solving those. And now we're looking at inequalities, which have to do with less than or equal to, greater than or equal to, strictly less than, strictly greater than. Pretty much a lot of it is similar to what we do with equations with the equal sign. There's certain things that we have to be a little bit careful of. Other thing that with inequalities, a lot of times in math, we like to notate things in interval notation instead of inequality notation. They mean the same thing, but a lot of times you're going to be seeing things like that, especially in calculus. And so being able to identify between the two is good. So interval notation, so let's look at inequality notation. So we have inequality, and we have interval notation. And then we also have a graph. Okay, so let's say we have x is strictly greater than a. So this, and sometimes writing it on the graph is first helpful. So basically on the number line, you're going to locate where a is. And once you find where a is, it's telling me x is bigger than a, so I'm shading everything that is bigger than that. So any number you plug in here that is on the right of a is going to make this a true statement. So then you need to decide, are we including the value of a or not? Since this is strictly greater than, we are not including a. So sometimes you have notated that with an open circle. Here, same thing, idea, but we're going to notate it with a parentheses. Parentheses means that you're not including that number, but you're getting very, very close to that number. And so basically what we have here is how we're going to write this in interval notation. So always moving left to right. So the smallest number on here, well, is a, but technically not a. So we're going to have the parentheses on the left of a. Comma, so always going, coming from the left where you're starting, comma, and then where are you ending? Well, since this is going on forever and ever and ever to the right of a, it's getting positive. It's going to positive infinity. Since infinity continues to go on forever and it doesn't stop at a particular value, we use the parentheses there. So only difference this had been if it was with the equal sign greater than or equal to a. When you drew the graph and when you write the interval notation, you're including the value a, and how you notate that is with a bracket. And so in here we can say interval notation, you're starting, the smallest value is a, you have a bracket because you're including, and again we're going to infinity, parentheses. So if we had x is strictly less than b, so you would go to your number line, you would figure out where b was. Since it's a number that is less than b, it has to be to the left of where b is. Determine if you're going to include b or not. If you do not include b, you use a parentheses, and if you include it, you use a bracket. Okay, so from left to right on that number line, we're coming in from a negative infinity, and we're getting really, really close to b on the left, but not ever hitting it. So a parentheses. Sometimes we have what are called compound inequalities, and that's where you have multiple inequality signs in there. So for instance, you might have a is less than or equal to x, which is less than b. So if I was to graph this, I would go to my number line, I would look at the number and try to figure out where a was on my number line. So let's say it was here. And then I'd determine where b was on my number line, and it is here. Well, this is telling me that every x, that number is between those two numbers, a and b. So we want to shade everything in between a and b, and we're trying to determine if we're including or not including our endpoints of that inequality. A has the equal to part under the inequality, so it's including it. We put a bracket. B does not, so we're putting a parentheses. And so in interval notation, we write it just kind of like we did our graph. Smallest value on the left was A. It included it, so I had the bracket, comma, and the smallest value is B, getting closer and closer to B, but actually never including it, so a parentheses. Let's say you were given, let's see. Negative infinity to infinity was your interval notation. So basically, that's telling you on the number line that you're including all of our numbers are part of that solution or will work. So really can't write that as an inequality, and you would just say all real numbers. So shorthand for real numbers, and you should just get used to what that looks like, is this capital R, but for that vertical line, there's two vertical lines for that capital R, and that means real numbers. So that's just notation wise. Okay, so there are certain properties of inequalities. So if we're given that A, some number, is smaller than some number B, it doesn't matter what we do. If we do the same thing to both sides, if we add a number or subtract a number to A, it doesn't change the inequality. So A plus or minus some number C doesn't change the inequality as long as we're doing it on the other side, B plus or minus C. So just really easily, let's say you had 2 and 5, right? I know that 2 is less than 5. Well, if you told me to add anything or subtract any number, this inequality would still be true. And so if I subtracted 100 from both sides of this equation, well, 2 minus 100, that's negative 98, is less than, well, 5 minus 100 is negative 95. Negative 98 is a smaller number. It's more on the left of the number line than negative 95. If I had added 100, 102 is still less than 105. So anything that we do, adding and subtracting, it's not going to change the direction of your inequality. So same thing if that had been greater than. So if this was A is greater than, sometimes I like to just do this. All of those symbols would have worked. What about multiplying? So let's choose a number. If I chose, and look at this number line, if I chose 5 and I multiplied both sides by 5, would that still remain a true statement? Well, if I multiply 2 by 5, that gets me 10. If I multiply 5 by 5, that gets me 25. Well, 10 is still smaller than 25. Any number that you told me, what about 0? That would be false. So we can't multiply 0 on both sides. That could change. If I added 0 to both sides or subtracted 0 both sides, that doesn't do it. Okay, now let's think about negatives. So if I multiply this by any negative number, you chose a number, didn't matter what it is. If you multiply both sides by -1, is -2 smaller than -5? If you look on the number line with your negative numbers, when you go to the left, they get, the absolute value of them get larger. So this -1, -2, -3. So -2 is actually bigger because it's on the right of -5. So this is false. So it ends up that we can do any property to inequalities and it will remain true unless you multiply, and it also division is just multiplication of the reciprocal. It's going to remain true. Okay, so basically we need the rule. If you multiply or divide, by a negative number, you must flip the direction of your inequality. Okay, so let's look at an example. So fill in the blank to form a correct inequality statement is the directions. And this says, if x is greater than 5, then -4x is what to -20? So look at this and see what are you doing to both sides of your inequality to manipulate that x is greater than 5 to get it as -4x is what to -20? You're multiplying by a negative, right? You're multiplying both sides of this equation by a -4. And so since you're multiplying both sides by a -4, this is flipping the inequality sign. And so instead of being greater than, it's going to be less than. Sorry. Let's say you had 3x plus 4. And this is greater than 1/3 times the quantity x minus 2. So solve each inequality, express your answer in set notation or interval notation. But we didn't talk about set notation. Okay, so we're gonna basically solve this just like there was an equal sign in there. And just worry about if we're multiplying or dividing by a negative, we have to switch that sign. I noticed that, so when we're solving linear equations, this is linear, we simplify both sides of our equation down. I can distribute the 1/3 inside the parentheses, but I don't like dealing with fractions. And so we could get rid of the fractions by multiplying by the LCD. Well, there's only one fraction there, and that fraction, the denominator is 3. So I notice if and that's a positive number, I could multiply this side by 3 on my inequality, then I would have to multiply this side by 3 on my inequality. So let's distribute the 3. And so I have 3 times 3x, that gives us 9x, plus 3 times 4, so that would give us plus 12, is greater than, well, that 3 times the 1/3 times that parentheses, that's strictly multiplication right there. And so basically, with that 3 here is going to cancel with this 3 in the denominator. And so we're technically left with 1 times the parentheses x minus 2, which is just x minus 2. So we're almost there. Just like a linear equation, we got all the terms with a variable that we want to solve for on one side, all the terms, constants in this case, to the other side. So let's subtract x on both sides of our equation. Oops. And let's subtract 12 to move the constant on the other side. Okay, so when we subtracted things, it didn't affect the inequality, so we're good. 9x minus 1x is 8x. Our 12's cancel is greater than x cancels, and -2 minus 12, that gives us minus 14. So get x by itself. We want to divide both sides by 8. So we're dividing by a positive number. So again, we don't have to worry about our inequality flipping. And so x is greater than, and you always want to reduce your fractions. And so I notice 14 and 8 both have 4 in common. Sorry, not 4, 2 in common. 2 goes into 14 7 times, and 2 goes into 8 4 times. So we get x is greater than 7/4. Negative is outside, so -7/4. So if you went on the number line, and if it makes more sense to you, this 4 goes into 7 once, so this is -1 3/4. So it's any number that's bigger than, strictly bigger, so not including, negative 1 3/4. So everything to the right would be bigger than that. And so interval notation, we're starting at, but not really including, negative 1 3/4. Have a parentheses because you're not including, and we're going all the way to infinity. So x times the quantity 4x plus 3. This is less than or equal to, parentheses, 2x plus 1, quantity squared. Okay, so just same thing with the equation, simplify both sides down first so we can distribute that x. Distributing the x inside the parentheses, we get x times 4x is 4x squared. Distribute the x to the 3, we get plus 3x. Is less than or equal to, well, that's 2x plus 1 times 2x plus 1. I'm going to do it down here real quick. Really, you should probably be able to do this without foiling all the time. So 2x times 2x is 4x squared. Our middle term, 2x times 1, and our other middle term is 2x times 1. So 2x plus 2x, that gives us 4x. And then our outer term, 1 times 1, so plus 1. So distributing that out gives us 4x squared plus 4x plus 1. Okay, so first thing I look at, and I see that this is quadratic, and we haven't talked about it, but I know quadratic equations or inequalities, we have to do it differently than linear inequalities. We have to do the process a little differently. But I also notice once we try to get everything to one side and we subtract the 4x squared, that now changes that to a linear inequality. And so I'm just going to go, we can go about it solving it as a linear inequality. It doesn't matter if you move your variables to the left or the right. Usually though, when students have variables on the right-hand side, they get them mixed up in which direction, and I do too sometimes, of where your inequality is. And so, but then also some students like to always keep the coefficient in front of the variable positive so they don't have to deal with flipping the inequality. It really is up to you. I'm going to keep my variable on the left. So I'm going to subtract 4x on both sides here to get the terms with the variables on the left. And so doing that, I get 4x squared minus 4x squared, that canceled. 3x minus 4x, that gives me negative 1x. Less than or equal to, well, my 4x squareds cancel, my 4x's cancel, and I get 1. And so this is where I have to be careful because I want that positive 1x. And in order to do that, multiplying both sides by a negative 1 changes this to a greater than or equal to sign. So I'm going to bring down my negative x and my 1. So this gives me negative 1 times negative x, which is positive x is greater than or equal to 1 times negative 1, which is negative 1. So any number in there that is bigger than or including negative 1 is part of our solution. And so if they wanted it and they didn't want us to graph it, we could do that. You're starting at negative 1, you're including with a bracket. and then comma, infinity. So I'm seeing a rule in here that I haven't seen in a college algebra textbook before teaching this, but I have seen it coming across in a different class. There's a rule of inequalities that if you're given that some value B, it's greater than some value of A, and this is greater than 0. So basically it's telling me that those two numbers, if that's a true statement, they're positive. So if I have some number B, which is bigger than A, and both of those are positive numbers, the reciprocal flips the inequality. So that would be saying that 1 over A is greater than 1 over B, which is still greater than 0. So positive numbers the reciprocal of those values flip the inequality. So sometimes just looking at things with real numbers make it easier to see. So let's just choose two numbers that are positive. So 5, and I need that number to be bigger than A. So let's just say A is 2. So reciprocal of 1/5, I'm sorry, I just said it. The reciprocal of 5 is 1/5. Let's compare 1/5 to reciprocal of 2 is 1/2. If it's hard for you to see which fraction is bigger or smaller, sometimes putting it in decimal form is easier. Well, 1/5 is the same thing as 0.2. So is 0.2 bigger than or smaller than, and 1/2 is the same thing as 0.5. Well, 0.2 is smaller than 0.5. And it just happens that it kind of is confusing because the 2 here and the 0.2, that just not, that's not a coincidence. That is a coincidence. Okay, so the number taking the reciprocal flips the inequality sign if they're positive. And then they have, if you have A is less than B, and it's less than 0, so if we're having a negative sign, then the reciprocal, 1 over B, is less than 1 over A, which is less than 0. So to me, it looks like either way, you're flipping your signs. Because if I brought this down, this would be saying 1 over A is greater than, flip the sign, 1 over B. And the inequality things are facing the direction correctly. So if x is less than or equal to -4, which is less than 0, then figure out the following. 1 over blank is less than or equal to 1 over blank, which is less than 0. So it looks like to me that they're taking the reciprocal. And so I just need to figure out, is 1 over x going to be smaller than 1 over -4? Oops, they have a negative out there? No, they don't. Well, I noticed that when I take the reciprocal, they switch. And so I'm going to put the -4, and then to make this true, 1 over -4 would have to be smaller than 1 over x. I just want to make sure I'm covering all types of questions. So what if you had 0 is less than 2 over x, which is less than 3/5? So there's multiple ways that we can do this. We can split this up as multiple inequalities. And because it's a compound inequality, it's an and statement. So it's like an intersection. Or we can kind of use that fact that we were just looking at. And so we can think of this and we can flip them. We want to flip these. And so we know that if it's a negative, 0 is less than this. So these are both positive numbers. So it's still going to be positive. But when we flip it, we're going to have x over 2. That was smaller than. It's now going to be bigger than 5 over 3. And these are still positive numbers. I don't know if that's going to work. So I'm looking at something that I like I said, I've never seen this portion in a textbook like this that I've gone over. I come back to that. Where did I pull that problem? Technically, how I would have gone about this in the, before is I would have looked at this, like I said, I would have broken this up as 2 separate inequalities. Let me just do that. I would have said this is the same thing as saying that 0 is less than 2 over x, and 2 over x has to be less than 3 over 5. And I think this is where there's a problem. I guess it's not really technically a problem. Notice here, if we multiply both sides by x, I get 0 times x is 0, is less than, those x's cancel, 2. That's always a true statement. And so So and means intersection. We have to take what they share in common. So now if I solved this inequality over here, I can clear the fractions by multiplying both sides by our LCD, which is 5x. Multiply this side by 5x. And so here I have 5x. The x's cancel, so 5 times 2 is 10. Is less than the 5's cancel, 3 times x, which is 3x. So solving for x, if we divide both sides by 3, we get x is greater than 10 divided by 3, 10/3. So a couple things you had to be careful here. If we didn't know what x was. If x was negative, that would have flipped my inequality signs. But if you go back and you use some reasoning, looking at our original compound inequality, notice that 2 over x had to be positive. It had to be bigger than 0. And so if x had been a negative number, that statement would have been false. And so I know then that x has to be a bit positive number. And so I'm okay with this not flipping the inequality. The other problem I would have had in this inequality is if my variable was 0, because I can't have 0 in the denominator. But again, looking at this, it says that this 2 over x has to be strictly greater than 0. So there's no number that I can plug in for x that would make that 0 or a false statement. So again, and we need to take what they share in common. And we have, well, x, and this is always true, and x always has to be greater than 10/3. And I tend to like, again, my variable on the left-hand side. The greater piece is with the x, 10/3. And so our solution, you can write an inequality like that, or it's everything that's bigger than 10/3 to infinity. And so I probably could have gotten that by what we were just kind of saying, now that I'm going back. If I had used our reasoning from above, right, that would have been because flipping it would have changed the inequality. We could have said x over 2 is now greater than 5 over 3. We could cross multiply. I get 3x is greater than 10, divide by 3, so x is greater than 10/3. So knowing that rule actually did take it, it was a lot faster. I am so surprised they don't have quadratic inequalities with this. So if we have 0 is less than parentheses 3x plus 6, in the parentheses, that is raised to the -1 power, which is less than 1/3. So remember negative exponents. Negative exponents, we make them positive by bringing what that negative exponent is, the base, down to the denominator. So in this case, the whole parentheses 3x plus 6 is the base. So 0 is less than 1 over 3x plus 6. That's now raised to the first power. I don't have to put it, which is less than 1/3. So here again, I can break this down into two separate inequalities and do an and statement, or we can use the rules of those reciprocals. And so if I take the reciprocal of this, that tells me then 3x plus 6 all over 1, which I don't have to write, then is greater than 3. Okay, x by itself, if I subtract 6 on both sides, so here I'm seeing an error. So if I subtract 6 on both sides, I get 3x is greater than negative 3. So x is greater than negative 1. Okay, I'm seeing a lot of things here. Negative 1. If I plug in negative 1, is that going to make this a positive number? Yes. So I'm okay here with plugging in negative 1 for x, and that's still a true statement because 3 times negative 1 is negative 3 plus 6. So this would give me 1/3. But 1/3 is not strictly less than 1/3. Okay, but that's okay because of my inequality sign. Okay. I don't think we're having a problem. Okay, I just wanted to look and make sure things looked okay. And so inequality notation, we're going from negative 1 and we're going to infinity. And parentheses around both. Actually, the one other thing I want to make sure is we can never have the denominator equal 0. So I just want to make sure. So we know that 3x plus 6 cannot equal 0. I just want to make sure that that doesn't fall inside of my inequality, my solution. So if I subtract 6 on both sides, I get 3x cannot equal negative 6. Divide, x cannot be by 3, negative 2. And negative 2 is not inside this interval.
So why'd you just drop the 0 when you went down?
Okay. Because I knew that that wasn't going to affect anything. If I solved this, I had then for this inequality, this would have given me 0 because if I multiplied this by the reciprocal. The thing is, I can't take the reciprocal of 0 because that would give me some number over or 0 over 1. 0 is really 0 over anything other than 0. And that would be undefined. And so the rule had to be, though, that that expression that we were working with had to either be strictly greater than 0 or it had to be, back up here, it had to be less than 0. And so I think they have that piece of the stipulation in there so that we can use those reciprocal rules. And like I was saying, this is a little piece that I didn't notice. Like, oh, I can do this, no problem. That I haven't seen before coming across teaching college algebra. And I really don't want to tell you how long I've been teaching because you guys might know how to do math. And I'm not that old. Okay. Really, when I started teaching, I probably looked like I was in middle school or high school. The first time I walked into the classroom to teach college, they didn't believe I was the teacher. Anyways, that was eons ago. Any questions? I should have paused the recording. Okay, so I think we just finished 1.5. I'll make sure I didn't skip anything, but I think I got through that. Let me see where we're at. So far this week, we've gotten through 1.1 through 1.5. That means that your homework due on Thursday by class time is 1.1 through 1.5. Again, you can always get in and do homework late, but it's knocking off 20% of that grade on that section of the material you didn't complete beforehand. When I'm looking at homework grades on the My Math Lab, I'm taking the average of so I'm taking your grade for each section, and then I'm taking the average of all of those scores, and that is your homework grade at the end of the semester. There's quizzes in there on My Math Lab that's kind of thrown in there with that too. Any questions? So before I let you guys go, and I am willing to stay behind and answer questions, and Laura, I'd love to talk to you too. Let me